So let's talk about a brand new function that we've never discussed before. And this function is very closely related to the exponential functions that we've been talking about. And the name of this function is a logarithm. And so let's begin by talking about the different pieces of a logarithmic function. So in a logarithmic function, this letter right here, this lowercase b that we put right here, is called the base of a function. And so whenever you read a logarithm, if I wanted to read this equation out loud, what I would actually say is log base b of x equals y. Log base b of x equals y. Okay, great. So what do the x and the y mean? What do we call these pieces? The most valuable sentence for you to remember about logarithms is that a log is an exponent. A log is an exponent. Now in math, we know the word is means equals. 2 plus 2 is 4 means 2 plus 2 equals 4. Is means equals. So when we say a log is an exponent, what we mean is that a log equals an exponent. So in this case, we have y as being the exponent of this logarithm. So the base is b, the y then would be the exponent, and that would make x just the answer to our exponential equation. And the reason I say exponential equation is because we can rewrite a log as an exponential equation. If we have a base of b with an exponent of y, that would be the same thing as b to the y power, and it equals x, the answer. So the base of b raised to the y power has an answer of x. B to the y power equals x. And you will be able to do this accurately 100% of the time, convert a log into an exponent, if you always remember the base is the little number, b, and the exponent is the thing after the equals. It's what the log equals is the exponent. So for example, if I did this, I'll do log with a little 2, 8 equals 3. So what are we saying here? Well, we're saying that the base is 2. This is a log base 2 of 8 equals 3. So the base is 2. A log is an exponent. The log equals the exponent. So 3 is our exponent. And that means 8 is going to be the answer when we write this as an exponential equation. So what are we going to write this as? 2 to the power of 3, the base is 2 and the exponent is 3, 2 to the power of 3 equals 8, or 2 cubed equals 8. This can be done with fractions as well, and it's really not even that difficult. Let's do log base 4 of 1/256th equals -4. If this was an exponential function, one of the questions I might ask would be, what power would I have to raise 4 to in order to get 256? But with a logarithm, it's already given to us. The base is 4. Log base 4 of 1/256th equals -4. A log is an exponent, so the exponent is what comes after the equal sign. A log is an exponent. And the answer is 1/256, 1/256th. So how do I write this as an exponential equation? Base of 4, exponent of -4, and it equals the answer, which is 1/256. 4 to the power of -4 equals 1/256th. So those are the basics of how to convert a logarithmic equation into an exponential equation. So that's one of the skills that we're going to need to know how to do is how can I convert from a log to an exponent? Something else we'll need to know how to do is how to go in the opposite direction. So if I told you 15 cubed, it's a very big number, 15 cubed is 3,375, could I convert this into a logarithm? And the answer is yes, as long as I know how to label my pieces. So in an exponential equation, this number right here is the base. This tiny little number up here, of course, is the exponent. And in this case, this big number, 3,375, is our answer. Okay, so base of 15, exponent of 3, and the answer is 3,375. How do we convert this into a logarithm? Well, it's going to be log base 15 of, well, it's always of the answer because a log is the exponent. We know the log is going to equal the exponent because a log is an exponent. A log is an exponent. So the only thing left to put here is the 3,375. And there we go. We've converted our exponential function into a logarithmic function. Let's do one more of these and then we'll try to actually solve some. We'll take some that have like a piece missing, see if we can figure those out. Let's do one with a fraction exponent or a rational exponent. 4 to the 1/2 power equals 2. Now you may recall that 4 to the 1/2 is the same thing as the square root of 4. That's how we used to do these with just using our exponents and our radical functions. But let's do this one using logarithms now. The base is 4. The exponent is that little 1/2. Our exponent. And our answer is 2. So when we write this out as a logarithm, it's going to be log base 4 of the answer, so of 2, and a log is an exponent, so the log equals the exponent, which is 1/2. So let's try to evaluate some. Let's evaluate some logarithms. And by evaluate, what I mean is if we're given a logarithm, can we tell what the answer should be? So log base 16 of 4, what is that? So what we mean is, what would the answer to this be? And let's do equals y, just because in our first example of the pieces of a logarithm, we wrote the exponent as y, it equals y. So let's just leave it like that, just for consistency. It doesn't really matter. You could use any variable you like, but we'll use y just to keep things consistent. Okay, so to solve this, let's rewrite this as an exponential function. So the base is 16, log base 16 of 4. A log is an exponent. It equals the exponent. And so then, of course, the only number left, this 4, must be the answer to our exponential equation. And so we're going to write this as 16, our base, to the y power equals 4. Okay, so 16 raised to what power is going to give us 4? So here we have to rely on what we learned in our previous unit about how to solve exponential equations. And one of the things that we learned with solving exponential equations is that we first need to make the bases the same. Make the bases the same so that we can make the exponents equivalent. So this 4 is the same thing as 4 to the first power. Could we rewrite the 16 so that it is also a base of 4? And the answer is yes, because 16 is equal to 4 squared. And so we can rewrite this as, instead of 16, we'll do 4 squared. 4 squared to the y power equals 4 to the first power. Great. Okay, so remember our exponent rules, power of a power. If we have 2 and y both as exponents, the way we put those together is through multiplication. So we've got 4 to the power of 2y equals 4 to the power of 1. And now that we are in a situation where our bases are the same, we have bases of 4 for both of these. If the bases are the same, that means the exponents must be equal to each other. They have the same base, they must have the same exponent. So that means 2y must be equal to 1. So let's solve for y. Divide both sides by 2. And we end up with y equals 1/2. 0.5 is okay. We'll leave it as y equals 1/2. Now if we go back and look at our exponential function, it makes complete sense. We were asking 16 raised to what power is 4? Well, 16 raised to the 1/2 power is the same thing as the square root of 16, and the square root of 16 is 4. So our answer does make sense in the context of this problem. Okay, let's move on and see if we can learn how to graph a logarithm. Okay, so now we've got our graphing calculator up so we can learn how to graph these logarithms. So let's go ahead and press the y equals in order to graph these. And in order to graph a log with a base of 5, we press the math button here just below the alpha button. And we're going to scroll down to option A that says log base. There it is right there, option A, log base. This is on the TI-84 pluses. There's log base, and we'll select log base 5, and then we'll put in x for our variable. And before we graph it, let's take a look at the table and see what's going on with the table. So I'm going to press second graph, and we've got a whole lot of errors here for negatives, and the reason why, remember, a log is an exponent, so we're taking the number 5 and we're raising it to a bunch of exponents and getting an answer. Now the x is the answer, so when we go look at our table, these x's of negatives mean the answer is a negative number. How can we take the number 5, raise it to an exponent, and get a negative answer? And you can't. You cannot raise 5 to any exponent and get a negative. So that's the reason why we have negatives as errors for all these, because you can't take 5 and raise it to a power and get a negative number. So I'm going to look at these that are just whole numbers. For example, 5 to the x of 1 gives us 0, but this means it's 5 to the power of 0 is 1. So if I were going to make an xy table to graph this, my first value of x is 1 and my y value is 0, and what that means is if I raise 5 to the power of 0, I get 1. Now the next whole number I get is 5, 1, so that means if I raise 5 to the power of 1, 5 to the first power is 5. Now I bet the next whole number I get is going to be really big, because if raising it to the power of 1 gives me 5, the next whole number is going to be raising it to the power of 2, which is going to give me 25. And there it is. The next whole number is 25, 2. And then cubed is going to be way beyond that, because 5 to the third power is 125. So I would have to go way, 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 way down to find my next whole number point, 125. And 3. So what this tells us about our graph is that much like our exponential function, this graph is going to change very, very rapidly. It's going to be a very rapid change with this graph. So let's go ahead and graph it and take a look at what we have. And it is similar in some ways to an exponential function. In some ways it's very, very similar, except it sort of flattens out almost immediately, because remember from our table, the x's are getting very, very big right here, but the y's are staying very small. So it doesn't get very tall as the x's get big, so the logarithm graph flattens out almost immediately. And so this is just a characteristic of logarithmic graphs, is that they flatten out really, really quickly. And if we wanted to go back to our table, if you wanted to find where the next whole number point would be, that's 5 to the power of 4. And we would have to go a long, long, long way to get, look, we're just now at 3.5 and we're in the upper 200s. It takes a long time Look how small the y's are as the x's are huge. These huge, huge x values, and we still have not hit a y value of 4. We're coming up on it pretty close. Oh, we're getting really close. There it is. 625 and 4. Because 5 raised to the power of 4, we can add that in our table if we want to. 5 to the power of 4 is 625. So these logarithmic functions get very, very large on the x-axis, but very, very small increases on the y-axis. Now this particular logarithmic function had a base of 5. Something tells me we would experience something much different if we changed the base. So instead of a base of 5, let's say we do like a base of 2. Let's try log base 2 of x. So I'm going to go back to y equals. I don't really need to change anything in here except just replace the 5 with the 2. So I'm just going to type right over that 5 with the 2, log base 2 of x. And now let's go look at the table. Now, if I go look at the table, it's going to be on that 619 or whatever that I stopped at when I was scrolling earlier. So I really don't want it to start there. I want to start back at 0. The way that you can do that, you see right above this window button, it says table set, TBL set, right above window. If I do second window where it says table start, let's make the table start at 0. And now whenever I go look at the table, it's back to 0. And so right away, I've got 4 whole numbers that I can see just on the main screen. So when I start graphing this one, my first point there is x of 1, y of 0, because 2 to the power of 0 is 1. My next number is 2, 1. 2 to the power of 1 is 2. Then I've got 4, 2. 2 squared is 4. And then I've got 8, 3. 2 cubed is 8. And the next one would be 2 to the 4th is 16, so I don't even really have to scroll down that far to get the next whole number. So this one still increases on the x much more quickly than it increases on the y, but certainly nowhere near as quickly as log base 5 did. Let's go ahead and graph it and see what this looks like. And that's much easier to see what the increase of this function looks like. So then those two both had a base that was a number greater than 1. Let's try one with a base that is lower than 1, log base 1/3 of x, just to see what the difference is. So let's press y equals, and we'll change our 2 to a 1/3. And we'll just see what happens when you have a base that is a fraction. So there's 1/3, log base 1/3 x. So this is taking 1/3 and raising it to a bunch of powers, which we know raising 1/3 to a positive power makes it a very, very small number, and raising it to a negative power makes it a very, very big number. So let's see what happens with that graph. And of course, as expected, flips it over. If we take a look at the table, we get negatives because there is no power you could raise 1/3 to. That would give you a negative number. Raising 1/3 to any power is going to give you a positive. And so the whole numbers here are few and far between. Raising it to the first power, of course, gives us 0. So 1, 0 seems to be a common point through all of these. And then we've got 9, -2. And our next whole number point is going to be quite a ways down. It's going to be 27, -3. And then after that, I'm sorry to say, our next whole number is going to be 81, -4, because that's the next, 4 is the next power that you can raise 3 to that gives us a whole number, 81, -4. So with all three of these that we've graphed, they all had 1, 0. Now, of course, that's not always going to be the case, because just like our exponential and radical and quadratic functions, these can be transformed. So let's take a look at one of these. F of x equals 3 log base 10 of x plus 1. Now, hopefully, we've done enough of these problems at this point where you can kind of guess what these numbers are going to do. Anytime you have a number added on to the end, this causes the graph to either raise or lower. In this case, it's a +1, so we expect this to shift the entire graph up 1. And then a number multiplied in front causes the graph to be either stretched or compressed. A number greater than 1 is a stretch, so this we expect to have a stretch by a factor of 3, meaning 3 times as tall or 3 times as steep or what have you. So let's press y equals and graph this and see what it looks like. So 3. Now log base 10 is a really common log, and the reason it's very common is because we count, humans do, in base 10. Log is so common that log base 10 is so common that we actually have a button on the calculator just for log base 10, and it's this log button right here. So when you see just plain log, that means log base 10. Now you can push the log base button like we've been doing and put in a little 10 there, and it's totally fine. But this log comes up so frequently and so commonly that there's a button for this. It's called the common log. There's a button for it that's just the log button. So log base x, and then we want to close parentheses around the x and then do a plus 1. Okay? So there's what that graph looks like. I'm not sure if it really did stretch it and shift it up 1 without comparing it to what it would look like if it wasn't the 3 and the plus 1. So let's go ahead and go down below it and let's just graph log of x. Let's see what it looks like without the 3 and the 1. Okay? And so the blue line is when it has the 3 and the plus 1, and the red line is without. And so then it's kind of easy to see, certainly it was stretched. Let's go look at the table and see what the plus 1 did. Oops, we're still on that 80 from the last problem. So let's go second window. Let's make our table start at 0. And then second graph. And so just from the very first whole number here, you can see that the blue line was 1, 1, and the red line was 1, 0. So the red line, remember, was just the plain log x. That one goes through 1, 0 like all of our logs have so far. But then the blue line went through 1, 1 because it was shifted up 1. Now if we go to the next whole number, the blue line went through 10, 4, and the red line went through 10, 1. Well, why is that? Well, it's because not only is it raised up 1, but it's also stretched by a factor of 3. So if you take the original from the red line, multiply by 3 and add 1, you get the 4. So that's where that comes from. It's multiplied by 3 and then add 1. And of course on the 1, 0, 0 times 3 plus 1 is just 1. Okay, let's take a look at another transformed one. F of x equals, let's do 1/2, so we'll do a number below 1 in front. Let's do one of our logs with the fraction bases, and this time let's put the number on the end inside the parentheses. Now again, hopefully we've done enough radical, exponential, and quadratic functions where you know what this does. This one, of course, same thing that 3 did, except because it's a number lower than 1, this is going to be a compression. So it's going to compress by a factor of 1/2. So it's going to be half as tall, or increase half as quickly. The -3 is perhaps the most confusing transformation in all of math, because the -3 makes it look like it's going to go 3 in the negative direction. But in the parentheses, it does the opposite. This actually translates right 3 units. This one translates right 3 units. Okay, so let's go ahead and graph this. Press y equals. Let's clear out both of these. So in the first one, the blue line, we're going to do our original, our transformed one. So let's do 1/2. And we're going to do log base a fourth. So math A, log base 1/4. And then all in the parentheses is the x minus 3. And then below that, let's do the one that doesn't have the 1/2 and the -3. Let's just do log base 1/4, just so we've got something to compare it to. So we'll do log base 1/4 of just x, and we're just going to use that as a comparison. Okay, so the blue line is going to be the transformed one, and the red line is going to be the non-transformed one, and we're expecting 3 units right and compressed. And so it's very easy to see from the graph 3 units to the right, the whole thing's been shifted over, and it's also pretty easy to see compressed. The blue line is shorter than the red line. So confirmed, translated right 3, and compressed by a factor of 1/2. We're going to finish up by talking about a practical application of exponential and logarithmic functions, and that is the Richter scale, which you're probably familiar with whenever we talk about earthquakes. We talk about what it measures on the Richter scale. Now, what you may not know about the Richter scale is that the Richter scale increases exponentially. A measurement of 2 on the Richter scale is not half as bad as a measurement of 4 on the Richter scale. Each number of intensity is 10 times higher. So a measurement of 4 on the Richter scale is actually 100 times worse than a measurement of 2 on the Richter scale, not twice as bad. An earthquake rating of 7 is 10 times worse than one measuring 6. And so the formula to calculate the intensity is a really easy one. It's 10 to the x minus 1 power. And x is the rating on the Richter scale. And that is a number from 1 to theoretically 10. I don't think there's ever been a 10 on the Richter scale. And then y is the measurement of intensity. Now, the strongest earthquake in the US hit Alaska in the 60s, I think. I want to say 63 or 64. Was a 9.2 in Alaska in the early to mid 60s, I'm pretty sure. Let's see if we can calculate the intensity of that earthquake. So going this direction is really easy. You just do y equals 10 to the, and then if the Richter scale was a 9.2, 9.2 is just like the most devastating earthquake. You just replace 9.2 minus 1. We would get 10 to the 8.2 power. Simple, right? And 10 to the 8.2 is some gigantic number, so I'm going to use the calculator to do 10 raised to the 8.2 power. It's going to be something in like over 100,000. It's going to be huge. Oh gosh, I was off by a lot. It's millions. So this is going to be 158 million. Good Lord. 158 million. 489,000. 319.2 is the intensity. That seems pretty intense. But let's go the opposite direction. Let's see if we could take an intensity and use an intensity to calculate what it would be on the Richter scale. How bad was the earthquake? How much damage did the earthquake cause? Could we turn that into a Richter scale measurement? And so in order to do that, what we want to do is take the original equation, y equals 10 to the x minus 1, and we want to find the inverse. And the inverse is what will allow us to take an intensity and calculate what the Richter scale would be. It's been a little while since we've done inverse. But the process is that we switch the x and the y. So instead of y equals, it will be x equals 10 to the, and instead of x minus 1, it will be y minus 1. And now we want to solve for y. So right away, we run into what before today would have been a really big problem. How do I get a variable out of the exponent? I have that y up in the exponent. How am I supposed to solve an equation if the variable I need is up in the exponent? But now we have a method for doing that, and that is to convert it to a logarithm. If we convert this into a logarithm, the exponent will come out of the exponent and into the regular problem. Why? Because a log is an exponent. 10 is the base. Y minus 1 is the exponent. And that would make x the answer to the exponential equation. So we will have log base 10 of x equals y minus 1. Because a log is an exponent, the log is going to equal whatever the exponent is. And now we just add 1 to both sides to get y isolated. Log base 10 of x plus 1 cannot be combined. We'll just leave that as log base 10 of x plus 1 equals y. And there it is. There's the inverse equation. So now if we knew the intensity of the earthquake, which is found using a number of factors, we could plug in the intensity to this equation and figure out what its rating would be on the Richter scale. And that's one of the uses of logarithms, is finding the inverse of an exponential function and using it to calculate the damage of earthquakes or the scale of an earthquake. Okay, and those are the basics of logarithms.